Topic today, delicate brute force. That's an oxymoron. I like oxymorons. They're more interesting. So computers are fast, so why not take advantage of their speed? But we need to be clever and resourceful about it. And so the first of the hard problems that's going to take brute force, delicate brute force, is setting specification limits. It involves overcoming a hard math problem. Find the largest hyperrectangle in the factor space whose interior points map to being within a compliance region of nonlinear constraints on the responses. Not easy. And we're going to find a way to visualize the factor space and map, take every point in the factor space, map it to the response space, find out if it's in specification, and find a hyperrectangle in that space that's safely compliant with respect to the responses. And the other problem is hierarchical clustering, especially for genomics problems, which are really huge. And it's going to involve brute force, but not so much like the brute force of Atlas, who is lifting the world on his own shoulders, but using a little ingenuity and being like Archimedes, who said, I can lift the world if you give me a long enough lever and a place for to put it. So let me introduce the first one with a little video of Julia O'Neill with an interview with Anne Milley on specification limits.
One of the issues that plagues pharmaceutical manufacturing, and one of my passions, is that it's typical in pharmaceuticals to set specifications based on process experience.
Oh.
And when we do that, and then we do a process capability assessment, we're making a circular calculation. So we set control limits or specifications based on what has been produced so far. We produce some more and then compare those results to what was produced in that initial baseline period. And we usually get a number close to 1, which is exactly what we'd expect to get. And it's not very helpful. So we really need to do better at setting specifications. And with all these advances in genomics and real world evidence, I think we are on the verge of setting specifications that are more relevant to the patient. There's a lot of work underway. The FDA has come out with a number of initiatives supporting that shift, but we still have a lot of work to do, but that is coming. And I do hear people, even within the pharmaceutical industry, moaning about, well, why can't we be Six Sigma? But until we set meaningful specifications, we're never going to be Six Sigma, because we're going to end up right about 1.
Oh, interesting. That sounds really important.
Very important. Yeah, I feel very strongly about that. And as I'm working with novel biopharmaceuticals, I keep pushing people. The scientists understand so much more about the products, the mechanism of actions, than a product that was developed 40 years ago. We didn't have all that knowledge. Now we do. So we need to start building it into specifications. And we also need to make sure regulators are comfortable with that, because it's a big change in how things are done.
Right. Wow. We'll keep making progress on that. That sounds like that's really important to make progress on.
So
one of the issues.
Now, the initiative she was talking about from the FDA is the Quality by Design initiative. And it talks all about spec limits, but they have a different vocabulary to talk about things like proven acceptable ranges and normal operating ranges and so on. But the very interesting concept in those documents is the concept of design space, the multidimensional combination and interaction of input variables and process parameters that have been demonstrated to provide assurance of quality. And working within the design space is not considered a change, but movement out of the design space is considered to be a change that would normally initiate a regulatory post-approval change process. Design space is proposed by the applicant and subject to regulatory assessment and approval. So that's design space. So the new concept here is that there's a model. We understand how the inputs make the outputs because we have a predictive model that we've done all the experiments, and we are using that model in order to find the best settings for the inputs to make the outputs. But let's help use that model to help set spec limits. So we start with the spec limits on the outputs, and then we inversely go through the model to infer some spec limits on the inputs. Maybe not uniquely determined, but at least some spec limits. Now, design spaces are not required to be hyper-rectangular, but if they are, then they're independently controllable. So we're going to try to find a hyper-rectangular part of the factor space that's compliant with the spec limits on the outputs. Well, that's a hard problem. And especially since the models are often nonlinear, and it's also non-uniquely determined. And so we're going to have to do something to picture that factor space, that hyperrectangle within the factor space that's going to lead to compliant responses. So how do we do that? Well, it's a hard problem. Here, for example, let's see, laser pointer. So here are the spec limits on the responses. We have a lower spec limit for a couple of them, and then upper and lower for the next two. And each of those responses is predicted by a quadratic regression expression, as you see here, estimated by least squares. And this is with the tire tread experiment, and we're exaggerating how precise the tire tread experiment is yielding. And we suppose that we have an error of this prediction equation with certain standard deviations. So now we have to invert these things in order to force a spec limits on the inputs. Well, not an easy problem. So let's go to JMP and see how we might approach that problem. So here's the data for tire tread. Let me open that and set some spec limits on it. And we can open the profiler, and with the profiler, we can see the spec limits on the axis of the profiler on the vertical axis. And we can actually see that, sure, with these desirability functions and the profile of the desirability functions, we can actually visualize what that might be like. And so we can we can move this one factor, and anything in that factor space or that factor interval will then be compliant if I fix all the other factors. And of course, that's the problem. We're not fixing all the other factors. We want a rectangle around all that space. So we can go up dimension, and here's a contour profiler, and we used all the spec limits to colorize the region. And so in this factor part of the space, silane by silica with a fixed value for sulfur, we can go up and make a shape. I'll start with an oval, change it to a rectangle, and now I can try to make that rectangle so it fits within that space, and almost got it there. So now if I keep my factors within that rectangle, I'll be compliant for the responses. But of course, the problem is that this is only looking at 2 of the 3 dimensions of the factor space. If I change sulfur to be lower, then the space opens up. If I change it to be higher, then I'm completely out of compliance. And so the contour profiler only helps a little. Okay, so how can we do it better than that? Well, the surface profiler can give us a 3D picture of all 3 elements of the factor space. And I have the spec limits set to these surfaces, on just the lower spec limits. And I can imagine building a hyperrectangle within those surfaces that's going to be compliant. But that's not gonna help me directly. So let's think about how to do it. Let's do that profiler again. And this time we're going to use a command in the profiler, output random table. And then what that's going to do is generate, in this case, 10,000 points that uniformly fill this factor space. And in JUMP 17 to come out next year, it's going to actually colorize the points on that with respect to satisfying the spec limits on the responses. It's going to make it red if it doesn't satisfy it and green if it does. And there are also some embedded scatter plot matrices where I can show that in greater detail. And here's that factor space. And here's the response space. And let's start without things being highlighted. The idea is that I'm going to go for the green. I'm going to find out some combination in all three factors that's going to light up the green here. And I can do that with some filtering, and that will help me do that. But I'm going to use a little trick. There's one modeling platform that's just for cutting up the space, and it's called Partition, named for cutting up the space. It's actually makes decision trees. And so here's the start of Partition. So it's got, of all the points in that factor space, that three-dimensional space, of those 10,000, only about 16% of them are compliant. Only 16% of them are green. But it's going to say that I can cut up that space, and here are the candidates for it. And I'm going to just split here with the best cut, and that's going to cut silane. So if I'm over here with silane above 43, I have a lot more green. It goes from 16% to 24%. And I can even colorize according to that. And so let's select that. And you see here in the factor space scatter plot over here, I've cut out a lot of the red points, and it's become a little more green sounding. And now I can take that and cut again. Let's split here. And now I go up to 33%. And if I select rows, I've cut it on silica, the low values of silica. And now I can cut again, split here. And now I've gone up to 52% of my space is good by having a limit on sulfur. So now it's cut in all three variables. And I can just keep on doing that until I find a space that's good enough. So I split here again, and it goes up to 61%. Split here again, goes up to 71%. Split here again, it goes up to 78%. And in here, I'm just cutting the end of the tree that has the highest compliance, 84%, and 92%. Let's make one more cut. And now I'm up to 95% compliant with all those cuts. And let's select the rows and see where I end up. And now you see the factor space is almost all green. In fact, the only points that aren't green, the out of spec red ones, are in the corners. And of course, this is the uniform fill rate of inspec. It doesn't have anything to do with probability unless you have the uniform distribution on the factors. So if you're aiming at the middle of this factor space, it's unlikely that you would be varying much from the middle in more than one factor at a time. So you're not going to get those corners. And so that's probably a pretty good set of spec limits to make. Moreover, I can look at the leaf report on that and find, here's the leaf label that describes that one that has the most compliance. And if I look at that, that leaf report shows shows these constraints, and after removing redundant conditions and grouping, this becomes spec limits. And now I have spec limits that I can trust that's going to have a high rate of compliance for anywhere in that spec limit space. So that's the idea. I fill the space, the factor space, uniformly with random points, random uniform points, and then I just cut up the space until I end up at a good place. But I was using a modeling platform to do it. The modeling platform wasn't particularly designed to do that. It was designed to fit the best model. But I used it, and I sort of like that space. I've covered about a third of the silica range and more than half the silane range, and a little less than half of the sulfur range. So it's fairly reasonable limits, and so I found it. So that's still the long way of doing things. Now we want to make a feature that takes advantage of that kind of thinking and does it more directly. And that's the design space profiler. So I make another copy of the profiler, and don't need this older copy. And I still have these uniform points around. And now I use a new command currently called design space, and that's going to introduce another profiler that has to do with spec limits. So in this design space profiler, the lower spec limit is represented by the blue vertical line and the upper spec limit by the green vertical line. And there's a blue curve, and that represents the in-spec rate of, how well covered are we? What percentage of those 10,000 points is within the in-spec is in the green area. And it's going to show that if I change the spec limits, I can improve that rate. And so I can change silica and give it a lower spec limit of a little bit higher value. And I can change sulfur and give it a upper spec limit there. And I've raised it from 16% to 32% in spec. And I can keep doing that. And there's a button here called Move Inward that will take the highest sloped increment and keep going inward until it has a spec range. And I'm happy with. We're up to 84, 87, 90, 93, now 95.5%. And so similarly to what I did earlier with that, and now I can connect it to the table and use this, and now it's representing the spec limits that I found here. And I can do trade-offs. I can say, well, I can't control the upper limit of sulfur that well, so let me loosen that by going down that changes that, and I'll compensate for it by making it a little stricter on silica. So I can play with all these limits until I have the kind of spec limits that I'm happy with. This is not so good. Okay, now it's better. Okay, so that's the idea. And now I can do that for any set of data. Here's some coffee data. Turns out that coffee data with these ingredients, the only ingredient that makes a big difference is methanol. And so raising the lower spec limit on methanol is going to be the trick to being high compliance. Although I can also do make sure I cook it a little longer as well. So here's an example, the peanut data. And here I can set upper spec limits for ratio and do much better and so on, and move inward on those things. But I have two categorical factors too, hydrolyze and pre-soak. And right now it's evenly distributed, all those random points across these two things. But I can just say, well, I'm going to pick just the low value of hydrolyze. I'm going to uncheck L2. And all of a sudden doing that raises it from 85 to 94. or I can check the pre-soak and just do the L1. If I do that, it raises it up to an inspect rate of 1. And so you can handle categorical effects with the same kind of thing. So let's say, so far I haven't added the random area in, but when I do the simulate points, I can add that random area in, and then given that random error, I can then get a more realistic estimate and move inward on this and eventually get my inspect rate, given those spec limits, to pretty high values. There's 97%. Okay, so that is solving the specification limit problem, a hard math problem with brute force, just making a bunch of points and filtering those points with a profiler. Okay, so now we've looked at one of the problems. Let's look at the other problem. And that's a computing problem rather than a math problem. And it all has to do with hierarchical clustering. So how are we going to do that? Well, the requirement is that some people, especially genomics users, have really big data sets. They have a lot of columns and a lot of rows, and they depend on hierarchical clustering to understand the structure in their data. And they usually do two-way clustering, both rows and columns, with a heat map in between them to make sense of the data. But they have hundreds to hundreds of thousands of columns and hundreds to thousands of rows. And hierarchical clustering is just too slow for those kind of large problems. So we need to make it much faster. So how can we use brute force to make it much faster? Here are the kind of data sets we have around in our playpen. And you can see here that we have up to 17,000 rows in some of these and up to close to 1 million columns on some of them. The first one has close to 1 billion cells in it. So these are truly large data sets. So let's take one of them, Morocco, and think about clustering the columns in it. It's about 500,000 columns, 194 rows. If I ran hierarchical cluster with FastWard on it, it's going to take 171,893 seconds, or almost 48 hours. That's not exactly an interactive step. We want to make it much faster. So first, before we go farther, let me make sure you understand what hierarchical clustering is all about. It's done by agglomeration. You start out with each point in a separate cluster. So we start with n clusters. If you find the two closest points and combine them to make a new item that replaces the two that we combined. And we keep repeating that, find the two closest items, join, repeat until we only have one item. And from all those joins, we construct a tree diagram of the joined points called a dendrogram. And various definitions of closest yield variations of the method. And we recommend Ward's method. It's the classic least squares approach using weighted Euclidean distances and combining by weighted means. And so here's a little video that shows starting out with each point in a different cluster represented by different colors. And when I run the video, it's going to move that control to gradually show how it's combining clusters. Now we're down to 33, 24, 21, 19, 17, 16, 15, 14, 11, 8, 6, 5, 4, 3, and then all the way down to 1. And so showing that this dendrogram represents that the joining of those by least distance. So and get it to the next slide. Now, the classic approach to doing that is the distance matrix approach, where we create an n by n matrix of distances between rows, and we find the smallest distance. We combine those, we call one the leader and the other the joiner, and we update the distances to the leader to all the other points. And we just keep repeating that until we end up with one cluster. Well, it turns out when you have really big data sets, that's very expensive. N squared m just to get the distance matrix, and then n cubed operations to find the minimum of n squared items n times. But it's actually not quite that bad, but it can get pretty bad. In genomics, with those kinds of problems, it's going to take forever with the distance matrix approach. So you need a shortcut. You need some ingenuity here. And it turns out that back in the 80s, a method was developed that was much faster called near neighbor chains, also called the conga line method. And I read about this from the writings of Jan Murtaugh in Yorkshire, England. But it turns out that it was an earlier reference, but it was in French, where I couldn't read it, by Ben-Zachary. And there's been a lot of recent writings on it by Epstein, who wrote the most of the Wikipedia article. And here's the text of the Wikipedia article. And it's very simple. You start out with a population of 1-point clusters, and then you have this stack, and you pick randomly one of the populations and you put it on the stack, and you measure the distance from the top of the stack to all the other points, and you find the closest one. And if it's already on the stack, the closest one, you can join it immediately. Otherwise, you push it on the stack and then find the closest one to the new top member of the stack, and you keep repeating that until you end up with one cluster. And with that algorithm, you don't need to calculate all n squared over 2 distances. You just need to find the minimum in each step. But even that, you can use a mechanism to make that fast, a near neighbor mechanism. And we used a KD tree, and this was done maybe 20 years ago to do the KD tree method of near neighbors, to do the near neighbor chains. And it takes some artful programming to do that. And that was done by Craig Hales years ago. And we call that method FastWard. And it produces identical results to Ward's method, but it's a lot faster. But for genomics problems, it's still not fast enough. They're hard to multi-thread, so you can't have all the compute cores working at the same time. And when the dimension gets big, lots and lots of variables or columns, there are much more efficient structures to find near neighbors. It turns out KD tree just does one dimension at a time, the one with highest variance. And so it can't represent very much of the distance. And so it has to do a lot of backtracking if you have a very wide problem. So we need a new method. And there's a rich literature of big data clustering, but I wanted something very simple. And so here's the idea that we came up with. And the important part of the tree is just the last few hundred joins. Before that, you don't care if it's strictly distance ordered further down the tree. And so if we can find a method that just combines near neighbors without following strictly ordered order, that's good enough. Fit for purpose, as an engineer would say. So what we're willing to give up is the opportunity for a joined item to be considered immediately for joining again in the same cycle. And it turns out we weren't the only one to think of this two-phase process. Here's an article about clustering algorithms for gene expression data by 8 authors. And turns out all these authors are from Nigeria with Nigerian names. And they referred to this two-phase algorithm used in a clustering method called Chameleon. Okay, so we weren't the first, but we're going to do a variation on that. So we construct this other kind of near neighbor tree called a vantage point tree. And for each point, we find the 10 nearest neighbors, or k nearest neighbors, where k is 10. And then we have k times n distances of pairs, and we sort them in ascending order. And we go halfway down the list. And for each pair, if an item is not already combined, we combine the two, yielding a new cluster. And if the result is small enough in that cycle, less than 400 or so, then we do the last few hundred with Ward's method to make the hierarchical part of the tree strictly ordered, even though the bottom part of the tree is not. And otherwise, we repeat the cycle until n is small. Okay, so good prospects here because vantage point trees are really fast, even though they're not multi-threaded. They're fast to build. And you can search them with a multi-threaded algorithm. So very efficient to search for thousands of variables. And of course, with hybrid Ward, strict hierarchy is not guaranteed, but at the upper level, they are. So great idea. What could go wrong? Well, Murphy's Law, if anything can go wrong, it will. And here's what went wrong with this idea. We tried this on the Barron data set, 20,000 columns by 7,000 rows. And here we focus on the columns. And after finding the 10 nearest neighbors for each of the 20,000 or so ones, we end up with about 201,000 distance pairs, but we remove the distances from the point to itself and then sort and take only the first half. So we got 93,000 of those pairs. And so then we just start agglomerating with near neighbors. And it turns out we were hoping to agglomerate a lot of them, close to half the 20,000 of them, but it turns out we only get 2,500 points. Not very much progress with a lot of work to do for that progress, all that the VP tree build and then the search for all those near neighbors. And it turns out that many points are very popular. One of the 10 nearest neighbors to many other points. So if you look at point 9460 at the top on the right, it's one of the 10 nearest points to 6,556 other points. And if you look at another one, point 18124, it's nearly as popular with also over 6,500 near neighbor catches. And that's why we didn't get a good yield on that cycle. And we can call these kind of overpopular points as Kevin Bacon points, referring to the Kevin Bacon effect. They're close to many other points. And we can only use a near neighbor search object once to join in a given cycle. A near neighbor item wants to join in a given cycle. So why are we getting such a poor yield on this? Why do we have so many points that are close to lots of other points? And it's not transitive either. Point 9460 is very near item 18399, but item 18399 is not near any other point. So it's not really a cluster. It turns out that high dimensional space is weird. And item 9460 is a row that has more zeros than other points. It turns out most of these rows are mostly zero, but especially item 9460, making it easy for lots of points to be near that item without being near other items that are near point 9460. So the near neighbor VP tree clustering will have difficulty in these kinds of cases for reducing the number of points, and it's inherent to the situations. There's no structural cure. So we'll come back to that in a minute. But let's go through some examples of some of those data sets I mentioned. Here's the Barron data sets on the rows, clustering the rows, 7,000 of them. It turns out that hybrid Ward works pretty nicely. It goes through 9 cycles and gets a pretty good yield. It gets 1,645 of them on the first cycle and 1,527 in the second cycle. And here you see the CPU times for creating the vantage point tree and searching it. And we end up with 222 after 9 cycles. And so that's pretty successful. But then we try the columns and take 12 cycles, and the yield is really poor, only 300 points or so in each cycle. And it's going to take forever to get it down to 400 points. So even after all this work and 16 minutes of work, we still have 12,000 out of the 20,000 to digest. So it was a failure. Here's another example, 135,000 columns by 6,200 rows. That's the eMaze data. And it turns out it works for that. Works pretty well. It takes 8 cycles for rows and 12 cycles for columns. And looking through all the demo data sets that we had, for the rows, there are a lot fewer rows in these examples, mostly successful, but a couple of failures. But for the columns, we have more failures than we have successes. So we're going to think about how to do that better. So before we do that, let me mention these vantage point trees for finding near neighbors. It's very simple, actually. You pick a random point out of your data set. I'll pick point 0. And then you find the distance from that point to all the other points. This is with the big class data set with height and weight. And then you take the median of all those distances to the other points to point 0. And anything inside that median distance, you put on the left for nearer points. Anything outside, you put on the right. And then you recursively do it. You pick a point on each side to be another vantage point, and then you make a tree out of that until you've digested the whole tree into a search tree. So turns out these vantage point trees have been researched by many people. And here's an example of a paper. Sergey Brin, Department of Computer Science, Stanford University, a graduate student there. And he studied VP trees and a lot of variations on VP trees. And, you know, this algorithms for doing searches might lead to a pretty good job. So we like VP trees. They're great for doing searches, but they don't have a way to do the near neighbor chain algorithms because they don't have a good way to delete points and add them back. So, but we can use them for hybrid clustering if we just solve this over popular points better. Well, let's do it by brute force. Instead of taking 10 near neighbors, let's take up to 150 near neighbors and make it adaptive to increase K if K is not big enough, and sometimes take more than half of the near neighbor chains and take more cycles. So just turning up the volume on the algorithm we already had in several ways and see if that works. So here's the barren columns, 20,000 things to combine. And it turns out that finally it's able to do it. It's taking 28 cycles to combine all those near neighbors. And but it's finally got it down and using a K of 150. So that's a lot bigger than 10. But it's doing it. And here's the resulting dendrogram of the transpose version of that data set. And you'll see that it's a very unbalanced tree. In fact, here you see most of the points are red and green, but in order to make them red and green, I'd have to make the number of clusters up to 44 of them before it splits off the red and the green. Because most of the clusters, most of the branches of the tree, until you get 10 down at the end, are just finding outliers down here at the bottom. And then finally, you got this huge cluster that finally splits at step 44. And this is showing at step 50. So lots of points look like they're the same. And then you have a bunch of outlying points in all the upper level clusters. So that kind of explains this Kevin Bacon problem we had with the overpopular points. So here's the algorithm. We start out K at 10, build the VP tree, find the K nearest neighbors, sort the distances, find the from the smallest distance to halfway, you join if it's not already joined. And after doing all those joins, if the number of items is down to 400, we're done. Otherwise, we keep going another cycle. And if the yield was poor on the previous cycle, we increase K to a bigger number, build the VP tree, and keep on going until we get down to 400 or so elements, and then we build it hierarchically. So here's the Barron time on columns where I track NK. I start out K at 20 and it grows up to 150 and then finally descends down when it starts getting near the end of the processing, and it's able to do that clustering. And here's the two-way view of Barron. And here's another example where it didn't need to increase K. This is breast cancer. And here's another example, giant island mice, 25,000 columns, 100 rows. And this time it did need to increase K, but it didn't need to do so until it got farther along. It was able to take some good steps and then needed to increase K for a while. And then here's the big one with almost 1 billion cells. And it did not need to increase K for the rows, but it did need to increase Ks for the columns. And it was able to take those steps. And so here's that biggest example. Here's 1 billion, almost 1 billion cells. Of course, we're not representing every cells because we don't have a big enough screen to do it, but it's showing it and colorized for looks like 8 clusters. Here's the Morocco data set, 500,000 columns. And it did take a while to do this, over 3 hours, but it was able to do it. And took a large NK to do it. And here's the thing with both dimensions shown. So if I plot the distances, if I take the distances resolved at each join for each step, and I compare that with what Ward's method does. Ward's method here is represented by the red, and everything is monotonic. You know, you start out at the right with 5,000 clusters, and then you combine, and it's a nice monotonic distance. Well, this is simulated very well separated data. And if I do hybrid distances, it tracks it pretty closely, and then it gets to the end of a cycle, and it's able to combine a few that were a little bit off track and so on. And near the end, it's less well-ordered, but then at the very end, it flips into hierarchical clustering, and it's pretty good. So hypothetically, this is going to work very well. Now, real data doesn't work quite as well, and so we're going to have some things that don't cluster in the same things. So here, the red is the fast Ward, and the blue is the hybrid distance. And so at the end of every cycle, it drops a lot in the distance, and then it combines them, and you keep having these cycles. And at the end of the cycles, it's going to flip into pure hierarchical. And so the final clusters, the final few hundred clusters are going to track very well with the pure Ward's method. So how well does it cluster? Well, here's the Barron rows for looking at 5 clusters, and it looks pretty good. There's a few differences here. You can see it's colorized by the pure hierarchical, by the fast Ward, and then we see how it clusters in hybrid Ward. And you can see here in the green, there's some of the blue, some that hybrid Ward, the fast Ward thinks are blue, but hybrid Ward thinks should be in with the green. And similarly, the green are invading the red space here a little bit, but it's reasonably good for this number of clusters. So hybrid Ward is still not fast enough. Some of those still took hours. How are we going to make it even faster? Well, we can reduce the dimensionality of the problem. Instead of taking 20,000 or 500,000 columns, we'll try to reduce that. And one of the methods that you can think about doing that with is principal components analysis. So principal components analysis is all about dimension reduction. It's rotating the data to a much smaller dimension while still maintaining the approximate distance between points. And that's exactly what we want. So principal components can really speed this up. But it turns out it's expensive. We have to calculate a singular value decomposition of a huge data matrix. So if I take that GTEx and takes the first 300 principal components, I can take the clustering time from 461 seconds down to just 3 seconds, an amazing improvement. But to take the singular value decomposition, it took 775 seconds to do it. So net, we're slower than we used to be. So it was a good idea, but we need that singular value decomposition to be much faster. Well, it turns out that someone thought of that. There was a breakthrough in 2011, and it was called randomized SVD, singular value decomposition. Halko, Martinson, and Trop. In fact, it unleashed a whole field of randomized linear algebra. And look at the title of this, Finding Structure with Randomness, another oxymoron. So turns out that you can write a script to do this in only a few lines. First, you make a matrix of random normal numbers. Then you multiply it into the columns of X. So you get a much narrower matrix, Z. Instead of having 500,000 columns, you have 200 columns or so. So now with that Z matrix that's a lot narrower, you orthogonalize it. And then you multiply it back into X, and you get this matrix called Y. And so Y now has just a couple hundred rows in it, and but still a lot of columns. And you take the singular value decomposition of that, and then you from that you take the U matrix out of it, and you multiply Q into it, and that gives you a U, and that U, S, and V turned out to be an approximate singular value decomposition of the whole thing. And then you can take the principal components just by scaling the columns of U, and those are the principal components. So it turns out to be a pretty simple algorithm. And if you want to know more about this, there's some great videos. Stephen Brunton. So if you do a search for randomized SVD Brunton, you'll find a great video tutorial on it, just maybe 10, 15 minutes long. And if you watch this video, by the way, ask yourself, is Steve Brunton right-handed or left-handed? So let's use randomized SVD and try dimension 50. Well, it turns out that doing that to reduce the dimensions, the total time is reduced by a factor of 6.7. So it is a lot faster. And the results look pretty good in this first example here. And you might try different dimensions, but it turns out that for this example, looks like 50 is good enough. It improves with more, but then you spend more to get that. So turns out it's still too slow. It's improved in some problems, but it's still not as speedy as we can make it. So it turns out we can make it speedier by multi-threading the matrix multiplications and using all those CPU cores. So without multi-threading, the randomized SVD on this one problem took 255 seconds. By multi-threading with 16 CPU cores, it's down to 32 seconds. And so depending on the dimension you take, you can make things really fast. And of course, with fewer dimensions, it's less good in approximation and so on. And here's an example that shows the trade-offs. Without doing the randomized SVD, it was taken about 750 or so seconds. With the SVD, with only 200 dimensions, you're much faster. With 400, you're still some faster. With 600, you're slower. Okay, so it's a trade-off. But the same SVD I do for the rows, it's equivalent for doing the columns, and so you can use for both. And this idea can be used in many other places as well, which we intend to use it to. So we invented a new method. We adapted the method for this Kevin Bacon point problem. We used randomized SVD. We multi-threaded. But next question is, are the clusters any good? Okay, they look good in some of those examples, but you got to try it out on a richer set of examples. So let's try it out on this 4,000 row, 131 column data set called answer anthropometry. So is it any good? Well, here's an example where the FAST ward, it's colored by the FAST ward, and you see the effect on the hybrid ward, and it's no good at all. There's some correspondence between the FAST ward solution and the clusters, the 12 clusters you put in for the other, but it turns out this hybrid ward is not very nice, okay? Now it does a little better when you reduce the number of clusters. So if I colorize it down to 4 clusters, then it turns out that it's not nearly as bad. So maybe the very top of the tree is reasonable, but it gets bad when you go from 4 to 12 somewhere. So that brings up the question, what is the right number of clusters for this data set? And we actually have a clustering criterion called the cubic clustering criterion. And it turns out that it's recommending the number of clusters for this data set is 1. And of course, you can use any method to get 1 cluster, and they're all the same. So maybe this data set just doesn't cluster very well. And that's the problem. Okay, so let's compute the cubic clustering criterion for all these big genomics data sets. Well, let's see. We do that by getting the covariance matrix across the column. That's already multi-threaded. And then we get the eigenvalues for that covariance matrix. Well, let's see. The covariance matrix takes n times m squared over 2. And then we end up with a big eigenvalue matrix. So for Barron, with 20,000 columns, 7,000 rows, the covariance matrix operations is going to be 1.4 trillion. And the matrix we need eigenvalues of is 202 million elements. That's not something we're going to do. So we're going to have to find a different way of calculating the clustering criterion. But we already learned how to do randomized SVD, and those singular values are the same as the square roots of the eigenvalues of that covariance matrix. So we can use that as the ingredient for the cubic clustering criterion, and all of a sudden just take 13 seconds for the Barron columns and calculate that. And here's the Barron rows, and then on the left and the columns on the right, and it's telling us I really need a lot of clusters, 30 clusters. For Barron, it's a little uneven for 27 clusters here, but it gets pretty good for 5 clusters. And then for the columns, you can see here that it's just clustering outliers. And so here's a close-up view of some of that. So if I use standardized instead of unstandardized data, I get a little bit different result. Looks a little better, actually. If I use this simulated data, you can see that the criterion has a huge bump right at 10 clusters, which is the way it was simulated. And then all these methods are generating perfect results for that clustering. So if you've got data that's well separated, it's going to do the job, and it's not a hard job to do. And it's pretty obvious how many clusters there are. So we needed hierarchical clustering, but it was too slow. We found near neighbor chains, that's still too slow. We invented hybrid clustering. We got the Kevin Bacon overpopular problem. We adapted that, still too slow. It worked, but it was still too slow. We found randomized SVD, still too slow. We multi-threaded that, and now it's pretty fast. But there are quality questions. So we needed the clustering criterion, but that was too slow. But it's much better now using randomized SVD. So going through all those steps, how are we doing on the benchmarks? Well, here are the times for those data sets on the columns. That's the wider, more challenging dimension. And the old method is in blue, that's fast ward. The new method is in red, that's the hybrid. And then when you add randomized SVD or PCA, that's in the green one, that's faster still. And so, yes, we're doing a lot of improvement here. Now notice that the scale on the bottom is logarithmic. And so if I go from 100,000 to 10,000, I'm doing 10 times better. And so going for the Morocco data set, it's doing a little better than 10 times better to do the hybrid method, and even better yet to do the randomized PCA on top of that. And in fact, all these things are doing quite well. Now, it's probably better to take the ratio of fast ward to these other methods. And here, the worst one, we're getting twice better. And the best one, we're getting about 23 times better than fast ward on the columns. And then if we introduce the randomized PCA, which are the red bars here, we can get up to 140 times faster. And so, so yes, it's worth doing these things. Okay. So one of our developers tried this clustering in R. They have a method called FastCluster that does use near neighbor chains. And it's supposedly the fastest in R. And to do this benchmark problem, it took 58 minutes. Now, fast ward and jump only took about 8 minutes. And the new hybrid ward took 22 seconds. That was on Jeremy's machine. So yes, we're doing quite good. Here's those times in a bar chart, where R is on the top with 3,465 seconds, fast ward a lot better, hybrid ward down to 22. And then if you use my machine with more cores on it, I can get it down to 7 seconds. And if I take the ratio instead of the times, the ratio of the method to the R, fast cluster in R itself, ratio of 1, obviously. Fast ward 7 times faster, hybrid ward 158 times, hybrid ward with more cores 232 times, hybrid ward with randomized SVD 517 times faster. So yes, we have plenty of ideas on how to make this faster yet, or to do better diagnostics and so on. So we have lots of ideas to pursue to further improve it, since sometimes it still takes hours. But we like the trend here. And it's valuable to get results quickly, even if it's a big problem. It keeps you in flow and allows you to do analysis in more ways, to make more discoveries, to understand what the data is telling you. And often there's a way to combine our fast desktop computers with some clever engineering to make even big problems finish quickly. And as always, we depend on your feedback to help prioritize what to work on, including what to make faster. You're frustrated at the speed of some of the things you do, tell us about it, and we'll try to make it faster. So, delicate brute force. Computers are fast, why not take advantage? But let's be clever and resourceful about it. So, that is my talk. Thank you much.